So now we're going to continue with part 2 of the question. We were saying that we have to figure out the shelf life for the packaging of 400 grams of cereals with 50 micrometer LDPE and 50 micrometer oriented polypropylene OPP. We said we're going to use this equation and that we have all the factors except the permeance factor. But also we have to figure out the vapor pressure of pure water at the respective storage temperature. Actually, this could be provided from the Google as a standard value, and when we will do any assignment or any quizzes next on, we will provide you with these standard values if needed. If it is assignment, you can figure it out from Google, as much of you has done, and that was good. But if there is a quiz, then these values would be provided for you as standards. The vapor pressure of pure water at the respective storage temperature of 25 degrees Celsius is equal to 2.376 centimeter Sg, which is a unit of pressure, unit of mercury, unit of pressure measurement. Okay. So now let's look again on the next equation that we said we're gonna derive out our permeance factor from. Area over P1 minus P2. We said that this corresponds to delta P, which would be the driving force, and this corresponds to water vapor transmission rates, or to the gas transmission rates of the film. How can we calculate the water vapor transmission rates? Actually, also there is no need to calculate it. We can get it out from standards from Google, and also you did this, which was good. For low density polyethylene, it is equal to 80 grams per meter square per day. For oriented polypropylene, and I again repeat at 25 degrees Celsius, it is equal to 1.35 grams per meter square per day. So over here we got the water vapor transmission rates for low density polyethylene and for oriented polypropylene. What are we going to figure out more? We need to figure out the driving force. The driving force would be equal to the vapor pressure of the pure water times the relative humidity of the storage condition of this plastic film. So the driving force would be equal to 2.376 times the relative humidity, which is given as a constant 75%. So it is 0.75, and the value would be equal to 1.782 centimeter Hg mercury. So again, how did we get out the driving force? We got the driving force by multiplying the vapor pressure of pure water, okay, times the relative humidity storage conditions that the plastic film is or would be placed under. How are we going to continue? Now we have the delta P, now we have the water vapor transmission rate. We can get out the permeance factor, assuming that we have no specific area conditions till now, because here we're not regarding the plastic as a specific dimensional package in this time, but rather we are regarding it just as a plastic film. Okay, so we're gonna assume, and we're gonna disregard the area factor. The area factor and this constant would be placed in the upcoming equation. It would be taken more into consideration. In this equation, we're gonna solve only for the permeance factor, which would be equal to the water vapor transmission rate divided by the driving force. This could be assumed, by the way. A lot of articles and a lot of examples undergone this assumption in order for simplification. And because the area factor would be anyway re-entered in the next equation. So the permeance factor for LDPE would be equal to 8 okay, as we have over here, over the driving force, which is 1.782. And this will give us an example, a value of 4.489 gram H2O per meter square per day per centimeter mercury. This is for LDPE. For oriented polypropylene, the permeance factor would be equal to 1.35 over 1.782, and it would have a value of 0.758 gram H2O per meter square per day, also per centimeter mercury. Now we got the permeance factor. We're gonna substitute it in the following equation that we said before. Also for LDPE, doing the substitution, okay, we have ln ME, we're gonna do the pseudo equilibrium that is used for shelf life calculation. It's 11 minus MI initial 2.5, I hope you are following up, over also 11 minus M critical, which is 8, is equal to P over X, the permeance factor for LDPE. We have already calculated it, 4.489 times the surface area, 0.06, also we calculated it previously, over the weight, 400 grams, times P0, that we found it also from the Google, 2.376, 2.376, over the slope B, 0.147, times theta. Okay, now for this, I'm gonna use this one. We will, after doing the calculator, I'm gonna obtain ln 2.8333, there's so many threes, equal, if we calculate all these factors together, 0.01089 theta implies the shelf life for packing 400 grams of cereals using low density polyethylene at 25 degrees Celsius and at a relative humidity 75% would be equal to 95.65 days, approximately 96 days. For oriented polypropylene, we're gonna do the same, also substitute with the equation and all the values, taking into consideration the permeability factor of oriented polypropylene, which is 0.758. Okay, and the shelf life would be 567 days. As conclusion, what can we say? The shelf life is inversely related to the water vapor permeances. So the shelf life is 567 days. However, the permeance factor is 0.75. And the shelf life for the low density polyethylene was found to be 96 days approximately, whereas the permeance factor was 4.489. So it's inversely related to the water vapor permeances of the film, and we can figure out that it is inversely related in a very nice way. I mean by this, low density polyethylene have approximately 5 to 6 times more permeance factor than oriented polypropylene. And if we look also at the values of the shelf life, oriented polypropylene have 5 to 6 times more shelf life than low density polyethylene. I hope you understood this example. We're gonna move forward into example 2.